Good morning, Ron.
Good
How are you?
morning. Very good.
Thanks to the Lord.
For the what?
I said, thanks to the Lord. I tried
Ah.
to translate
No.
your canonic response. Uh,
I'm wondering, where is your dog?
my dog is sleeping over there. He's sick of being a celeb.
Okay.
Last time we ran into some numerical problems. Let's share the screen and remind ourselves what's the problem and try to solve it, okay?
Mhm.
So I'm sharing my screen. Oops, yeah. This is a conversation with you, and this is our notebook. I just want to remind that on any relevant lessons in YouTube, in the description part, you can find a link to this notebook, to the code we're writing. Here in the this is the function f, our approximation function, and it is a very simple one. It is composed of two operations. One is just linear multiplication of two matrices, the weight matrix and the x's, the images. And the next operation is, we called it softmax, which is just exponential and normalization, right?
Okay. Let me just remind the speaker, whatever, the audience, that W is the current system of weights of. You're looking for the good W. That tells you what.
You're talking about W now, right?
Yes. So you're looking eventually for the good W, the one that will give you distinction between a cat and a dog.
The optimization is over W. We're looking for the best W, the best fit.
Yes. You're now calculating F on the current W. So you have certain W and want to improve it. So you function.
Exactly. We have a current approximation, a current W, and we try to
change it, to improve it.
The return here is actually, we can call it a prediction, because F is trying to be a predictor for whether it's a cat or a dog, right?
Yes.
Okay. So it's a prediction with a specific W, our current W.
The current W.
And can you remind the audience also what was the problems we ran into last time?
What you guessed was that you tried to somehow, how do you say it, to normalize by subtracting a number from everything, which is okay. You can do that in general.
This is you're talking about the solution now, but
no, that was the problem.
The problem was that when we use exponent on the logit is the name for the result of the linear operation, and logit was composed of very large number, and e to the power of that large number
overflowed. Yes.
Yeah, we have a problem of overflow. Let's just illustrate it again. So in order to illustrate it, we'll do something. We'll run only the relevant code, just a minute. We'll take X and Y and W from here. This is X and Y and W, and I have a problem here, just a minute. Indentation problem. And now let's do this. F of W and, oh, sorry, I'm in Hebrew. Okay. f of w and x. If I run that code, we have a runtime warning, invalid value encounter. Okay, he doesn't like it. If we'll show what the result is, oh, just a minute, sorry. You see, we have numbers like this, not a number, right? A very small number here. We have numerical problems. So you started telling us, let's first, let's do it more explicit. We'll make the calculation ourselves. We'll do, instead of calling f, let's do it this way. I'm trying to make it as clear as possible what the problem is and the solution. Instead of calling f, I'll write its implementation here, and I will write it like that. Okay? I expand. Okay. I'll remove the comments. So I did it explicitly, and I want to solve it. But before I solve it, I want to print, like, let's print what print logit max. I want to show the max element of logit. Okay?
Let's see it.
Let's show it.
The max among all 400, how many elements there are in logit?
We have in logit, it's a
no, a huge number. It's a 2 by 240 times.
240,000 numbers, right? In logit.
Yes, yeah, after F, yeah.
So this
200,
was the maximum number. It's around 2,500.
This is the maximum, so not that big.
It's the maximum of logit after the linear operation.
So the maximum is 2,000 something.
Yeah, 2,000 something. E to the power of 2,000 something is clearly an overflow, right?
Yes, of course.
So let's think about a solution, and I will draw it. Just a minute. If I have a softmax, we had a notation for softmax like that of a vector like x1 until xn. Okay. The definition of this operation is it's also a vector, right? In the same size, right? So yeah, I'm drawing with the mouse. I will write here. So in the j place or in the I place, we have e to the xi, right?
Yeah.
E to the xi divided
by the sum.
We normalize it by the sum, right? So a sum of we call it j, e to the power of xj, right? Yeah, right? That's the definition.
Yeah, yes, but 1 minute.
Yes.
You're working on vectors of size 2. What do you write there?
Right. In our case, it's only 2.
Yes.
Yeah, right. it's the number of categories, and we have only dogs and cats, and it's 2. But generally speaking, this is softmax, right?
Okay, yes.
Sorry for the messy. What will happen if I'll add a constant to all the elements of this vector? I will add C to all of them.
Mhm.
Will
So
it
you
change
multiply
the
each by e to
softmax?
the you
Right?
no, because you multiply e the
Yes, it
element
is
by
easy
e
for
to the
you.
c. You
It is
multiply.
easy for you to see it because you're a mathematician,
Great
but
mathematics. What do you mean?
let's show it explicitly. So I add a constant oh, sorry. I add a constant to all the elements in the vector, and I want to show that it doesn't change the softmax at all. Because what happens, I will just
You
write it.
multiply and divide by e to the c. Yes.
Yeah, and it's cancelled, right? So it's e to the c on the numerator and the denominator, right?
Yes.
And it cancels. So it's e to the c multiple by e to xi.
Mhm.
And because of the distribution, how do you call it? Distributed.
Distributivity.
Yeah.
Okay.
So e to the c here multiplied by this sum. So that's xj. So if we add a constant, it doesn't change the softmax, right? This cancels, right?
Yes.
Everything is clear. So
No,
we're
it's
going
not
to
so
use
easy to. So you want to subtract a constant so that there will be normal sizes. So not e to the thousand,
exactly.
but
I
e
want
to
to
the
make
5. But you have a
exactly.
problem because you want, if you subtract 2000 from everything, then the small numbers will be e to the minus 2000. What will you do with that? That's also
Good point. Good point. But look, here we talked only about a specific vector, a specific sample.
Yes.
We're going to do it for each sample. And that won't have the effect you were saying. Let's see.
Or actually, you can say that you can round small numbers to 0. It doesn't really change everything. If you have e
Yes,
to the minus 2000, just define it. And anything below e to the 100, e to the minus 100 will be a 0. And it doesn't affect it. It's okay for you.
yes, but I don't. But you're right. But I want to do it for each sample separately because I don't want a big number in one sample to affect the numbers.
Yes, so we do it separately, of course.
Yeah, we'll do it separately. I just want to remind that X is a matrix of all the samples. Each column is a sample, right?
Yeah.
So let's do it. Before we program it, let's do a playful example just to see what we're doing. So I'm opening a new one. Let's say that X is a very, very simple matrix, NP array.
Remind me, what is NP? N is a number. Is a number NP?
Pardon? NP is the NumPy library we're using. And this is just a way for me to create an arbitrary matrix, an artificial one. I'm writing a very, very simple matrix. Let's say we have very, very simple X. This X has two samples. One is 1 and 3, and the other is 2 and 4, right? Because the columns are, okay. So this is X, and I want, if I just do this, max, the maximum number is 4. If I do something like that, x minus the max, I will get something like that. But this is not what I want, right? I don't want to subtract the maximum from all. I want to do it column-wise, right? Are you with me?
For a second, could you have a break for 1 second? ¿Sí? לא נגעתי שוב פה. תנסי להפעיל שוב. כן, אבל אני אתחיל מההתחלה. לא, אבל אם תלחצי רק על הימני. Sorry.
Okay. So,
yes.
What we did here is not what I want. I subtract the maximum value 4 from all the elements, but I want to do it column-wise, right? For each sample separately, right?
Yes.
So we can do something like that. The max function also can receive an axis parameter. And this tells it to do max column-wise. So you see, for the first column, the maximum is 3. So for the second column, the maximum is 4. And if I do that, x minus the max per axis, this is exactly what I wanted, right?
Yes.
Okay, so let's change the implementation of f. Where should we do it? After logit, right? Before we do exponent, we'll do logit. Let's something like that. Logit dot max axis equals 0. Does it make sense? You remember what that sign means?
Yes, you subtract this number from the old number, and
Exactly.
So this is 2 dots. How do you call it? When I read
it's just a syntactic sugar, a shortcut for doing the old minus the new.
And putting the new, replacing the old parameter by the new one. Okay.
A more explicit way of writing it will be logit equals logit minus what I've written here.
Yeah, that's in old. That would be in old.
That's an explicit way of writing it. It's the same thing. Okay, so it makes sense what I've done. I just want to emphasize one thing. When we did this, can you see that the dimension did not match? The dimension of x max is what? Let's remind ourselves. X max is 3 and 4. It's just 1 by 2.
Okay, yeah.
And x is 2 by 2. Why
Yes.
can I do a subtraction like that?
Because
you remember?
There is a term for it. He broadcasts it. I'm very good.
Broadcasting, right? Broadcasting. It just multiplied. It's just for convenience reason. So the NumPy library making a broadcast. Okay, so where were we? So this should solve the problem, right?
Not sure. Let's see.
I can also erase this. This was another broadcasting issue. We put it because also the dimension here doesn't match, but the broadcasting solved it. So I'm deleting it. I think, and also I delete this comment because it's clear, right?
Yeah.
Okay. Great. So I think we solved one problem.
We tried.
Yeah. Of course, let's try it. So instead of explicit, I will just call it here and see if it's working. So f of w and x. How should we, let's look at f and see if it's look better than before. I'm running it right now.
So capital F is a 1 by 200 vector?
It's 2 by 120,000. It's 2 because it's binary predictions. Sorry, by 200, sorry.
Yes,
It's
200.
2 by 200 because we have 200 samples.
Yeah.
That's K, right? Okay, we don't see, we do see a none here. We found a bug.
Because it may be a too small, but perhaps, I don't know what to do with things
Maybe
small.
it's an overflow of two small numbers.
Underflow.
Underflow, yeah, it's also possible, but I didn't expect that. So we found a bug that I didn't expect.
In that line, you see there e to the minus 112, which you don't want.
Which is kind of small, right?
Yeah.
Yes, so...
But can you distinguish between this and 0?
Yeah, I guess the problem is that we need to say that it's really small number.
Round it down to 0, yes.
Yeah, round it to 0. I don't want to do something without thinking. This was came as a surprise to me. I was thinking about solving another numerical issue that we will bump into really shortly. But because it's a surprise for me, I want to think about it. So let's finish our lesson for today. I will think about it and we'll continue next time, okay?
Okay. Do you have anybody to consult about it or a book?
I have many sources to consult. For example, I have ChatGPT who told me the solution. Here, this is a conversation between me and ChatGPT. He knew the solution.
You're a true leader. Okay.
It's a very well-known issue, these numerical problems. Also, I put a link here to a dedicated post someone wrote about the same issue exactly. So it's not something people didn't think about. But this specific problem was new to me. I will think about it.
Okay.
So thank you, and we'll see each other next time, okay?
Yes. See you. Bye.
See you. Bye-bye.